Okay, so yeah, so let me say a little bit about the course. So anyway, my name is Yves L'Esperance. I'm a professor at York University in Toronto, Canada, and I'm visiting faculty here this year. Um, so yeah, so this course is basically an introduction to reasoning about action. And we're gonna mainly focus on a particular logical framework for this called the situation calculus, which is more or less a first order logic framework. Um, and and I'm going to discuss various representational problems with reasoning about action, and what's various reasoning problem that we may want to solve. Okay. Another thing I will do later in the course is discuss how we can represent programs for agents, essentially complex procedures, including loops and that kind of thing for specifying the behavior of the agent. And usually these will also incorporate non-deterministic choices. So it will leave the agent different options for how it should behave. Okay. And we'll talk about how we can reason about this. And then finally, I will talk about domains where you have non-deterministic action or effects. So basically, like for example, flipping a coin, it can fall on head or it can fall on tail. So if you want to represent this, essentially, you can think of the environment as choosing the outcome. Okay, the agent throws the coin, but the environment decides whether it will fall one way or another. It's just an example, but it could be a robot tries to pick up some object, but maybe will be successful, but maybe the object will fall on the table. Okay, so there's two possible outcomes, and we want to be able to represent the fact that this action may have different outcomes. So this is non-determinism. So these are the main things. And then if there's more time at the end, we might cover other topics related to, reasoning about action. So yeah, at the end of the web page, there's some suggested papers. So if anybody here wants to, or a team, maybe 3 students want to give a presentation on a topic related to reasoning about action, then again, you can talk to me or talk to Professor Di Giacomo to arrange that. Okay. And these are some possible topics, but I'm open to other suggestions as long as it's within the topic of the course. Okay. So yeah. So anyway, if you have any questions, raise your hand or stop me and ask me the question. I'll do my best to answer. Posso parlare un po' in italiano, ma è un po' non è molto buono, allora ok. So let's go to the lecture notes. Sì.
A small clarification about the exam. So we are supposed to do a presentation about the topic we choose, do it in class, right?
This is what so are you an elective in AI or in, yeah. So I think that this is one option for the evaluation. There may be an exam too, I don't know. I mean, Luca, Professor Yocchi and De Giacomo are kind of in charge of the evaluation for this. But if you want to do something about reasoning about action, then you can coordinate with me. Okay, but if you want to do a presentation, maybe with some other students in a team, maybe the right thing to do would be to write to me and Professor De Giacomo, and you know, you say what you want to do, and we can arrange it. So here you have my email, which is, you know. And if you're taking the PhD course, then I guess you have to talk to me mainly, but maybe again, you see Professor De Giacomo because he knows the rules a little bit better. So, okay, so let's start with this lecture. Okay, I hope everybody can see this. Okay, so yeah, so this is the outline of the first lecture. Basically, first we're going to talk a bit about the knowledge representation problem that an AI agent is facing, and then we'll go and discuss a specific logical framework for reasoning about action that you can use to, you know, represent the problems that the agent is dealing with, and possibly the agent can, you know, use this to make decisions, okay, about act to act. And then I'll talk more specifically about the problems that an agent that wants to decide what to do is facing, okay, that he has to solve in order to make good decisions. And that's the reasoning about action part, okay? Okay, so in this work, I mean, we're taking a particular approach to building intelligent agents, okay? And this is the knowledge representation approach. So the idea is that you want to build a system that knows about the world it's operating in, and can use this knowledge to act in a good way, okay, in a way that is good for him, okay. And so the key elements of this is that we want to represent knowledge explicitly in a formal language like a logic, okay, and so symbolic, and basically when the agent wants to know something, it will reason with this knowledge to see if you know, it can answer, say, a query, a yes/no query, depending on whether the query follows from what he knows, from all the sentences that it has in its knowledge base, or not, okay? Or maybe the negation of the sentence followed, and he would know that, no, this is not true, okay? Or he might not know either way, okay? If it does not follow and the negation does not follow, then he doesn't know. And you can also use reasoning to, you know, answer what question. So who is the president of the EU, or, you know, those kinds of questions. So reasoning is used to extract knowledge, consequences of this knowledge, and also essentially the agent can ask queries about what actions would be good if I want to achieve something, okay? And also an action or a sequence of action that I can execute. And then if the answer is yes, or if it can extract a particular action or action sequence, then the agent can choose to do that, okay? So this is a way that, you know, this reasoning can be used to deliberate, think about how to act, you know, in a way that will achieve the agent's objective. Okay. So I don't know if I can move this a little bit. Anyway, I think so this knowledge representation approach, or if you want knowledge-based systems approach, it's actually a rather radical idea if you think about it, and it's relatively recent. Okay, now it comes, it follows for many, a lot of work over a long period of time. I mean, it's, as I said, it's based heavily on reasoning and represent things in a formal way, so in a logic. Okay, so Aristotle is the first one who kind of proposed this a notion of logic and using rules of reasoning and that kind of thing. Then there was Leibniz that proposed the idea that thinking is a form of calculation. Okay. Then Frege developed the modern notion of symbolic logic. There was the work of Church, Gödel, and Turing that sort of related logic and computation and kind of defined some foundations for computer science, but they really didn't yet think about logic as a way of representing knowledge, the knowledge that an agent would use, okay? It was more like computers can be viewed as what can they do in terms of logical reasoning. And then the first person that really came up with this idea of knowledge-based system, which is to represent the knowledge that the agent has in a logic and use reasoning to decide what to do, it was John McCarthy kind of at the end of the 50s. In a paper, in particular in a paper on programs with common sense. And actually John McCarthy, together with Pat Hayes, is kind of the originator of the situation calculus. So you can see that this framework that we're going to talk about, it dates back all the way to the very beginning of AI. So what can we kind of observe about this idea of knowledge representation as a knowledge-based system? It's basically that we should focus on identifying what needs to be known by the agent to behave in a smart way and represent it using some formal language, okay, as sentences, and then do reasoning to use the knowledge that we've put in, okay? And so, so this is very different from the kind of approach that you use in, say, in deep learning, where you show a lot of examples and you let the system kind of extract some sort of very compact representation from all these humongous number of examples, and then it can, you know, can classify new example, or it can tell you what the value of function for what the output should be for some new input. Okay, but there's no explicit representation of what the system knows. Okay, so these systems are hard to explain. It's sometimes they make errors that are a little bit mysterious, that kind of thing. So knowledge-based system, you could say that one advantage is that, you know, you wrote down what they know, so they should be, in principle, it should be easier for them to apply what they know in a new context. Okay, so if you change the task that the system has to do, but it still knows the, you know, what the layout of the lab is, what the different rooms contain, that kind of thing, then should be able to adapt more easily to the new task. Okay, maybe even come up with a plan to achieve a new task. And also you can teach them more things simply by writing more sentences that you add to the knowledge base that the system has. Okay, so they're easily extensible. So this is kind of in contrast to also, I mean, you can imagine, you know, I want to get my robot to deliver coffee in a hallway where there's different offices. I can just write a C program to do that. Okay, that doesn't use the knowledge base or anything, and that should work. And it might even run faster than a knowledge-based system approach. Okay, but if you change the task a little bit, then you have to rewrite the program completely. If some, you know, if an office becomes, you know, a closet or a machine room, then again, you have to rewrite the program. You cannot just change one sentence or two that says this office is or this room is an office, and from that to this room is a machine room, and get the behavior to automatically change. Okay, so that's kind of the idea. If you think about it, it's quite I mean, it's quite a neat idea, but at the same time, the big, you know, challenge there is to ensure that the reasoning that the agent needs to do on this knowledge can be done efficiently enough. Also, you know, how do you get the knowledge in this knowledge base? Okay, for a very simple application, you can get some, you know, programmers to write it down, or people, I mean, advanced programmers that know logic to write it down. Okay, but generally, if you use a, you know, non-computer expert, you may have to design some tools that help them write things in a way that you know, the system in the right notation, you know. So there's some challenges with this kind of approach as well. And it generally, I mean, there was a period especially in the 90s, 80s, that where expert systems were very, very popular. Okay, but then over time, I mean, companies found that it was very costly to develop them and to maintain them, because you had to add experts in the areas, I don't know, medical experts or expert in you know, configuration of systems and so on, working together with PhDs in computer science to, you know, develop the system and the knowledge that you put in the system. Okay, so now the wind has shifted a little bit to machine learning techniques, where you can some kind of get some data that you already have, you know, put on the web or whatever, collected somehow, and then get the system to try to learn something from there. But it's not necessarily something that is understandable by humans. That you don't necessarily get a a logical representation. Okay, so to illustrate why we want to do reasoning about action, let's look at the reasoning like a running example. Okay, so suppose we have a robot, we'll call it Self, that lives in an environment where you have various rooms that are connected by doors, and the doors can be open or closed. And some rooms are control rooms, and they contain a button that allows the agent that is in this room to open all the doors. Okay, so one example of this is suppose we have a layout with 3 rooms, A, B, and C. Okay, the control room here, there's only one, it's room B, and this contains the control button to open all the doors. There are doors between room A and room B, and between room A and room C. Okay, initially the robot is in room A. The door between room A and B is open. Okay, and but the door between room A and room C is closed. So that's the initial state of this this example. And so here basically the robot can move between rooms. Okay, and when it's in a control room, it can press the button to open all the doors. Okay, so these might be useful to achieve certain goals that this robot or tasks that we give to this robot. And so here we can represent what the agent can do, the robot, the actions that it has that are available to it. So one is to go to a room, okay, go to a room X. So here there's a precondition for this action that there must be a door between the room where the agent is now and the room X. And also this door must currently be open. Okay, so this is required if the agent is to be able to do the action to go to room X. Okay, what's the effect? Well, basically that after this action, the agent is in room X. Then the other action that we talked about is to open all the doors. So you can only do this. So the precondition is that the agent needs to be in a control room. Okay. If this is the case, then he can do this agent, and the effect will be that all the closed doors get open. So in order to open all doors, the agent would have to first go to room B, and then he can press the button, open all the doors, and then the door between room A and room C would become open. Okay. Any questions so far? Okay, so how do we represent this symbolically? Okay, so we might start by thinking that we're going to have a certain number of predicates that don't change value. Okay, they're static. So these tend to be like typing predicates. So here we might have a predicate room that says that its argument is a room. Okay, another one control room that says that X is a control room. So if this is true, then it's X is a control room. A third three-place predicate door might say that there is a door between room X and room Y. Sorry, X is a door that is between room Y and room Z. Okay. And then you might have some dynamic predicates that change value as the agent acts, okay? So one might be the door is open. X is an open door. And then this one says that self in X means that the robot self is in room X. Okay, so if we now we can, given these predicates, we can define a model in this I don't know, first order logic language. Okay, using these predicates that represent the initial state in our application. Okay, so to represent this little world, we might say, well, here the rooms are A, B, and C. So here I is a first order logic model. Okay, you can think of it as a relational database. Okay, and so the interpretation of the predicate room is the set of three objects A, B, and C, which are rooms. Okay, the interpretation of control room is the only room that is a control room, that is B. Okay, the doors, well, we have two doors. Let's say DAB is a room that connects room A to room B, and AC is the door that connects room A to C. Now, here, this relation door, we can think of it as being symmetric with respect to the rooms that are connected. Okay, if you can go from A to B, you can go from B to A. Okay, so that's why the same door connects B to A here. Okay, and now for the dynamic predicates, so here, DAB is open, but DAC is not. Okay, so our interpretation says that the only object in open is DAB. Okay, DAC is not there. The rooms are not there because they're not doors. Okay, open only applies to doors. And then self-in is the relation or the predicate that is true for what room the agent is in. It's A. Okay, so this is a model in first order logic that represents this particular state of this domain. Okay. Now, instead of using a particular model, we can also use theories. Okay, so theories are simply sets of axioms, sets of sentences. Okay, so as I said, in the previous case, this is a bit like a database. Okay, here room is a one-place relation, door is a three-place relation, and so on. If you're using theories, then you write sentences. Okay, so here's a theory that essentially is satisfied by the model that we talked about on the previous slide. Okay, so this says that X is a room if and only if X is A or X is B or X is C. Okay, here you can, normally you would write this in logic by saying for all X, room X if and only if X is A or B or C. Here we're going to assume that if there's a free variable in sentence, automatically there's a for all that variable outside. Okay, so everything is universally quantified by default. Okay, then we would have a sentence that says that X is a control room if and only if X is B. So this means that B is the only control room. And similarly for the doors. So the only X, Y, and Z that are in the door relations are if X is DAB, Y is A and Z is B, or Y is B and Z is A. And similarly for the door from A to C. Okay. Then here we say that X is open if X is the DAB, if and only if, and self is in X if and only if X is A. Okay, so if I take this theory, the only model that this theory has are essentially models that are isomorphic to this. Okay, to this because here, so in some sense, I know everything that about the state of the world initially. Okay, it tells me for every relation, every predicate, whether it's true or false. Okay, now sometimes robots know everything about their world, but not always. Okay, maybe you know, the robot you know, he knows that somebody was around, you know, previously, so maybe he doesn't know whether the door from A to C is open. Maybe it is, maybe it's not. Okay, so if I want to represent this, then I would change this to say only open DAB. Okay, because this is equivalent to saying for all X, if open X, then DAB. So this says that the only open doors are DAB. Now I don't want to say that. Maybe DAC is open, maybe not. Okay, so I want this direction. So I want to say if X is DAB, then X is open. Yes, this I know. But for this one, in one model, it's open. In another model, it's closed. Okay, so the agent doesn't know. Now, maybe he could have a sensor to find out whether it's open or not. Maybe he can try to go through and it will succeed or not. Or maybe he could just go in the control room, press the button, then afterwards for sure will be open. Okay, so so that's one advantage of using theories is that you can represent incomplete knowledge, incomplete information. This is the main use that we do of, you know, theories in AI, okay, to represent incomplete information. Why don't we just use databases? Because databases only capture complete information, essentially. But if you want to represent, you know, disjunctive knowledge, or like here, either the door from A to C is open or it's not open, then you want to use a theory. Okay. Okay, so how do we kind of specify formally this domain? Okay, we have this robot can move from room to room and so on. So here I'm trying to write down the preconditions and the effect of these two actions using first order logic. Okay, so for goTo, I might say that for this action to be executable, the agent has to be in some room R, and there has to be a door D between room R and room X, and this door has to be open. Okay. What are the effects? Well, afterward, the robot himself will be in room X. And also, you will no longer be in room R. Okay, so essentially, there's no other room R which is different from X where the robot is in. Okay, so maybe initially he's in room A and we want to go to room B. So afterward, he'll be in room B, but he will no longer be in room A. Okay, because you cannot be in two places at the same time. So both of these are effects of going to room X. Okay. In some sense here, this effect of no longer being in the original room, it's implicit. It's not that you say I'm going from room R to room X. No, but you can find out that currently I'm in room R. So and then for open all doors, how you specify the precondition logically? Well, in order to do this action, the agent has to be in a control room. So we can say this by saying there exists an R, which is and the self is in this room R, and room R is a control room. Okay, so if this is true, the agent can do this action. And what are the effects? Basically, we want to say every door that is currently closed will be open afterwards. Okay, so here we have a little bit of a problem. So in the effect of this open all doors, we have to talk about two different states: the state before the action and the state after the action. Okay, so here we will see that, you know, in the situation calculus, you can easily talk about those different states. But here we kind of say, well, it's sort of like you want to talk about the state S that is the current state and the state S prime that is after the action, and say that some things from S are no longer true in S prime, and some things that were not true in S are true in S prime. Okay, how they change, how they relate. And one way would be to use this notation pre. So this would say that for every door, if D is closed in the previous state, then it will be open after the action. Okay. But this is a bit informal. Okay. Another problem with this this formalization is that you say what changes, what are the effects of doing the action? What changed when? So here I'm saying that, you know, when I go to X, I'm no longer in the room I was, and I'm in this new room. What about the doors? Are they still open or not? It doesn't say anything about that. Okay. I mean, intuitively, we would want to say that nothing except what I wrote down in the effect changes. Okay, so if a door was open before, it's still open after I go to a different room. If it's closed, it's still closed. Okay, similarly for open all doors, it doesn't change what room the robot is in. Okay, it doesn't change which are the rooms. Okay, which doors connect which room. Okay, so this nothing else changes, which is not explicitly written here. It, you know, it's important. It includes a lot of things. So we'll see that this is a key problem representing this notion of nothing else changes in reasoning about action. So any questions so far? Okay. Well, I think that you know, in logic, basically, we'll see that. I mean, the fluents can have different truth value. Okay, so these are the fluents. So the predicate that can change value. So which room I'm in and which doors are open, these will change after an action. Might be different from before. So if you do a sequence of action, they may change many times in the you're going through many states. Okay, so you know, these, if you think of these sentences here, they don't tell anything, say anything about what doesn't change. Okay, and if you think of these states as being different parts of your theory, okay, well, your sentences you put in, they didn't say anything about that things don't change. Okay, so they could change. In logic, not like in a database where you have everything. If something is not, if a tuple is not a relation, it's false. Okay, but in logical theory, if I don't say anything about whether it's sunny today, then it could be it's sunny, it could be it's not sunny. You have to say explicitly. Uh, so so that's the thing here, where you want to use logic to represent things, and so this issue of you need to have a way to say nothing else changes. Okay, if you just write this, you're not talking about it, then it could be everything changes. It's just not specified. What is the connection? When I go to a new room, it's not specified what happened to the doors, to whether they open or not, that kind of thing. Okay, so let's look at a particular formalism for reasoning about action, which is the situation calculus. So I said that, this was originally proposed by John McCarthy, and the ideas were kind of refined by McCarthy and Hayes. And more recently in the 90s, I guess Ray Ryder is somebody that did a lot of work on this formalism to develop kind of solutions to many reasoning about action problems. Okay, so the textbook, it's on the web page, and it's in the references at the end of the slide that you can look at if you want more details about this formalism. Okay, it's a kind of standard reference for situation calculus. So so what is the situation calculus? Well, it's a first order language, okay? And it's multi-sorted in the sense that you have different types of predicates and function symbols and, constants, okay? You can think of it as a kind of type first order language, okay? And the other thing too is that it uses this domain of situation, okay? And situations is a kind of, they kind of represent the state that you can reach, okay? They're like a tree. So these are defined inductively using a second order logic formalization. Okay, we'll come back to that. But for now, just assume that you have this domain of situation. So what are the types, the sorts? Okay, well, you have objects. So these are things of interest in your domain. So rooms, doors, and maybe the robot himself is an object. Okay. You also have actions. So these are, operation that takes the system from one situation to another situation. So, and these are represented by function symbols that may take arguments. Okay. So go to X is an action. Open all doors is an action. The object here, they're all represented by constants, okay? But you could have function symbols that return objects. Okay, so these, in general, these will be terms, they're object terms, action terms. situation, they represent a state and the history that led to that state. So we'll see more details about this in a bit. But for short, you can think of a situation as a state. Okay. And then you have fluents. Fluents are properties of objects that may change from a situation to another. Okay. So how do we represent these dynamic predicates, these fluent? Well, we use predicates where the last argument is a situation. So you can say that, self in room A in S0, the initial situation, and self in room B after some action. Okay. So everything clear so far? Yep. So let's talk a little bit more about situation. So situation, we can take them as representing state that results from a particular history. So doing a sequence of action starting from the initial state gets you to a particular situation. Okay. So in some ways, you can think of situation sort of like list of the actions that have been done to get there. Okay. So how do we represent situations using terms? Okay. And these terms can contain the initial situation as 0. Okay. And or they can contain you can use a function symbol do with 2 arguments. One is an action and the other one is a situation. And do AS represent the situation that is the result of doing action A in situation S. Okay. So so here, consider this example. So suppose I have this situation term. Okay. What does this represent? Well, this represents the situation where I started in S0, okay? The agent went to B, okay? Then he opened all the doors. Then he went to A, back to A, and then he went to C, okay? So as you can see, basically, the situation kind of stores the sequence of action that have been done in sort of reverse order. Okay, so that's why I was saying it's sort of like a list of action. Okay, so this basically, now in this situation, I mean, we can say that where's the agent? He's in room B. Okay, because he went to B. The last action he's in room C. Because the last action he did was to go to C. Okay, and now suppose that we consider a situation where you don't do open all doors. So you first go to B, then go back to A, and then go to C. What's the problem with this? The problem is the door. Okay, the door between A and C is closed initially. So unless I open all the doors, it's still going to be closed. So I cannot go from here. I mean, after doing go to A, I'm back in room A, but I cannot go to room C because the door is still closed. Okay. So so if you delete this part of the situation, you get a situation that is not realistic. Okay, because you cannot really execute the action that you would have to get to that situation for real. Okay. Okay, so now if you look at these terms, these situation terms, so you can imagine that what could I do in S0? Well, in fact, the only action I can do okay, is, I cannot go to room C, okay? So the only action I can do is to go to room B. Okay, I mean, if I had another action that says sleep, I could just stay where I am, okay? Once I'm in room B, what can I do? Well, I can go back to room A because the door is open, or I can open the door, okay? Once I've opened the door, then I can go back to A, and now I can go to B, okay? Or I can go back to, I can go to C, or I can go back to B. Open the doors again. I mean, so you can think of, there's a tree that represents all the actions that the agent could do, okay, starting from the initial situation. And some of these are not really executable, but so like the ones where I just, the situation, go to C as 0, that's not executable because the door is closed. Okay, so and so essentially we will see that there's an axiom in the that we can use in that actually defines this infinite tree of situations. Okay, it basically says that every situation corresponds to a list of actions, and every situation corresponds to actually a finite list of actions. Okay, starting in S0. And so a situation is kind of a sequence of action, but also it represents the state that is the result of doing that sequence of action. So the fluents have certain value is in that situation, which might be different from the previous situation in the sequence or from the initial situation in the sequence. Okay, and so fluents, so these are predicates that have values that vary from situation to situation. And so here we, in the situation calculus, so we would write, to say that the door is open, we would have a situation argument. So we would say that the door D is open in situation X. Okay. The agent self is in room R in situation F. Initially, so in S0, the only open door is DAB. In S0, in the initial situation, the agent self is in room A. Okay. But if I look at the situation, for example, do go to B as 0, okay, what has changed? Open X in do go to B, okay, as 0 is still the same. It's still only the door from A to B. But self in X, do go to B as 0, it's true only if X is B, because now I'm in room B. Okay. So this is how you can represent the dynamics, the changing state in this language. Okay. Essentially, you have these terms that represent situations or kind of state with a particular history. And you can say, this predicate is true for this argument in this situation, and it's false for this argument in this other situation. So self in A is true in S0, self in B is false in S0, but if you look at the situation, do go to B as 0, so after the agent goes to B, then self in is B is true and self in A is false. Okay, I mean, that's what we want. Okay, because if the agent, as we said, the agent can only be in one place at a time. Okay, so the theory should tell us that. What else do we have in the situation calculus? Well, we also have a distinguished predicate, okay, pos AS, and this is used to represent the executability of an action, okay? So we saw in our informal overview that, the actions going to and open all doors, they're only possible under certain conditions. Okay, so we can express these conditions using pos AS in the situation calculus. So here we would say that, so I mean, if it is true that pos go to B as 0, this means that the robot can move from whatever current location he is to room B. In fact, this is true, okay? Because, the robot is here, the door is open, okay? So, and B is connected to room A. So he's in room A now, he can go to B, and afterward he will be in B. So you have, pos B, pos go to B as 0, this should be true, okay? Pos go to C as 0, should that be true or false? False, because the door is closed, okay? Pos go to A as 0, should that be true? I mean, intuitively it should be false, because here we can look at okay, so here it turns out to be false. Why? Well, because there's no door connecting A to A. Okay, so similarly, the atomic sentence pos open all doors as 0 says that, the agent can push the button to open all the closed door in situation as 0. So this is not true. Why? Well, because you can only do this action when you're in a control room. In S0, the agent is in room A, which is not a control room. Okay, so this should be false. Okay, and so this is the whole language. Okay, so you have fluent, you have object and action, then you have fluence and situation. Okay, in general, sometimes people have functional fluence, and so fluents that are function as opposed to predicate. But here, every function you can represent it with a predicate and add that it's functional. So it doesn't really add anything. And you could have also non-fluent predicate or function, but here we're not, you can always represent a non-fluent by a fluent, okay? Just add a situation and say it never changes. Okay, so how do we, use the situation calculus to formalize, to specify these actions that we're talking about? Okay, this is what we had before, like in English. So in the situation calculus, go to X, we can say that, you know, it's possible to go to X in a situation if the agent is in some room R in situation S, and there's a door from R to X and it's open in F. Okay, so notice that this is similar to what we had before, okay? But it's different because now we're saying explicitly what the situation is. And we have this new predicate that says pause action situation, okay? Similarly, for open all doors, we can say open all doors is possible in S if the room that the agent is in S is a control room. Okay. Actually, it should say control room RS. Okay, so there's a typo here. Well, I guess you could say that they are non-fluent. So here, let's see. Okay, so here we only have these fluent. So the others are kind of non-fluent predicates, right? So yeah, you can say it's static, and so that's fine. The effect. So go to X. The effect is that after, so this says that the self is in room X in a situation that is the result of going to X in F, if and only if there's something missing here. It should be basically if X is F, or yeah, I mean, this is just supposed to be an effect specification. So this says that, you know, the agent is in room X after going to X in situation S, okay? And also, it's not the case that there's a room R different from X where the agent is in that room after going to X, okay? So this basically just specifies what changes, okay? So you're do go to XS, you're in X, and you're no longer in any other room, okay? For open all doors, if the effect is if the door is closed, if a door D is closed, so for every D, if a door D is closed in S, then it's open in after you do open all doors F. Okay, so you know, here you can see that I mean, close here is just not open. Okay, so if you're not open and you do open all doors, you become open. Okay, so here and notice in this example, so there's two different situations in this sentence. S is about prior to the action, and do open all doors. S is after the action. Okay, so you can talk about both the situation before the action and the situation after the action. Okay. So this is why, you know, why you can express the fact that if I go to B, okay, and I press the button to open all the doors, then this room will be closed, will be open. This door will be open after in do open all doors F. Okay. So, so essentially, this is our a specification in the situation calculus of both the precondition of these actions, okay, and the effect of these actions. Okay. Any questions so far? Yep. This arrow or? It's material implication, so it's implied. Sometimes people write an arrow, okay? So in this for logic notation, we use this, it's sort of like set inclusion, but it's really implied. Okay, and actually P implies Q is the same as writing not P or Q. Okay.
The second fact, shouldn't we also put US quantifier any D dot close DS?
Here we assume that whenever you have a free variable, there's a universal quantifier. So here this says actually you're right that for every D and every F, if it's closed, D is closed in F, then in the situation that follows doing open all doors in F, D is open for every D and every F. Any other questions?
So the FS situation problem, we have when the situation before, what do we have after the application? But in this case, no, yes, with the situation that we had before, the action over the
We'll see how you specify everything. I mean, this language allows you to talk about many different situations, many states that the agent might go through. Okay, and so I mean that's one reason why it's good for specifying planning problems. Okay, so if you could only talk about what has actually happened, I mean, when you plan, you think about the future. What are my different choices of action sequence I could do, and what would be true there? Okay, I want to find one that gets me to my goal state. Okay, so we're thinking hypothetically, how could the future go if I do different things? Okay, and so we want to talk about many different possible future states. So this is essentially what the situation calculus allows you to represent. Okay, that you start in a particular situation as 0, okay, and there are many possible branches, action sequence you can do with it would get you to different situations. And each of these situations may have different fluent, true, and false. Okay, some of them are like your goal is satisfied, some of them are not. Some of them are good, some of them are terrible. Okay. So you can think about the future and where you can go in the future and try to find the path that gets you to somewhere nice. Okay. But also you can think about which ones are bad and how to avoid going to things that are bad. Okay, maybe you have many goals. Okay, so now the second problem that we mentioned was here they don't say that other things don't change. So for example, for open all doors doesn't say that the robot doesn't move when you open all the doors. Okay, it doesn't say that you don't get new doors appearing. Okay, similarly, this effect axiom for goto, it doesn't say that goto does not affect whether the doors are open or closed and whether you know you have doors between some room or not. Okay, so it could be true, given what we wrote there, could be true that when the agent goes to B, a door appears between B and C. Okay, or it could be that here, I don't say that go to doesn't affect which doors are open, so it could be that simply by going to B, C open, or not, it doesn't say. And so if we want to be able to reason about what can really happen, we want to say that nothing else changes. Okay, so that's the frame problem. Okay, so to really know how a world changes, okay, you need to know which fluents are not affected by performing an action. Okay, so here we have some examples of statements that say that something is not affected. Okay, so when I open all the doors, if the robot is in room R beforehand, he's still in room R afterwards. Okay, so this is saying that the room that the agent is in does not change when you're opening all the doors. This one says that if a door is open in S, then if the agent goes to X, its door D is still open. It's not affected. Okay, and if it's not open, it's still not open. Okay, so these are usually called frame axioms. So they're a little bit like effect axiom, but they say what doesn't change. So the frame axiom, the effect axiom, it sort of says, well, I'm in room A before, and now I'm afterwards. After I go to B, I'm in room B, and I'm no longer in room A. Okay, but here you have the same thing on both sides. Okay, so you have open D and S and open D and do AS. You have self in S and self in do AS. Okay, so this says that this doesn't change. So why is this a problem? Well, the problem is that you need a lot of these axioms, these frame axioms that says that things don't change. Okay. In fact, if you have a more realistic example, okay, there will be very few actions that affect the value of a particular fluent. Most of the actions will leave things unchanged. Okay, so for example, think about the fluent color, that some object is a particular color. Well, picking up something or opening a door or using the phone or turning on the light or electing a new prime minister, this will not change the color of the object. Okay, so this fluent is affected by almost nothing. Okay, that can no action. So if you had to enumerate all this, then you would end up with a huge number of frame axioms. Okay, even if you could, write a program that generates them all, then this means that in your reasoning, this will be slowed down by all these axioms, or it could be slowed down by all these axioms. In general, you will need, for every pair of a fluent of an action, you're going to need a frame axiom in most cases to say that this fluent is not affected by this action. And you need two axioms, actually, one to say that if it's true, it remains true, and one to say that if it's false, it remains false. So, so there's been, this frame problem has been a key problem that has been examined in reasoning about action. There's been a lot of attempts to address it, in fact, by sort of considering this as a kind of reasoning by default, okay? So basically, if you think of, you know, some attribute being set to something by default, okay, this is sort of saying, well, unless I know something else, then, you know, I will set it to this value. So maybe if you have a Sapienza student, well, by default, he lives in the province of Rome, okay? Yeah, there are some exceptions that may live in other provinces, but, you know, they're rare. So it's a good default to have, okay? So, you know, one idea for dealing with nothing else changed would be to say that by default, fluents don't change, okay? And if you want to have them change, then you have to say explicitly, yeah, this action makes this fluent change from this to this. Okay, this is what the effect axiom says. Okay, but actually to make this work, it's quite difficult. Okay, so there's been a lot of effort, plus these logic, you know, I mean, that have been developed for doing this kind of default reasoning or non-monotonic reasoning, defeasible reasoning. So there's sort of logics where you can say, well, if I don't know anything, I will assume this. But if you tell me more and it contradicts, so like, you know, say there's a student, John, I know he's a student at Sapienza, I would say, where does he live, Rome? Okay. Then I find out he lives in Florence, then I remove my previous conclusion, okay? Because otherwise you cannot live both in Florence and in Rome. Okay, otherwise I would have a contradiction. And in first of the logic, if you have a contradiction, everything is true. So everything follows. So that's not good. So basically, so these logics are not straightforward, and the reasoning in them is complicated. The definitions of you know, consequences are complicated, and so on. So but as I say, people have really tried to use these things and develop them to deal with the frame problem. But in the 90s, I guess Ray Ryder proposed this solution to the frame problem formulated within the situation calculus. And actually, this is a pretty simple solution. Not completely general, but and it can be used to implement agents and so on. So let's look at that solution. Okay. So in what sense does it solve the frame problem? Well, what it does is it defines, for specifying both the effect and the non-effect of an action, it uses one axiom per fluent. And these are called successive state axioms. Okay. And then for specifying precondition, it uses one precondition axiom per action. Okay. So this is pretty compact. Okay. It means that you don't have this huge, you know, this quadratically many frame axiom. No, you just have, and you don't need the effect axiom anymore. You just have one successive state axiom per fluent. Okay. And then for the precondition, I mean, it's more or less what we had before. Okay. So because frame problem deals with the effect and non-effect of the action, not when the action is possible. So, and another thing too is that this solution it doesn't produce successive state axioms that are very, very long, because that would be a problem, you know. You could say, well, you get rid of all the frame axiom, you know, 2 to the n, where n is the number of, no, n times a square, okay, 2n times a square, or no, 2n times a, so it's quadratic in the number of fluent slash action, by having one but very, very long axiom, or one per fluent very, very long axiom. So that wouldn't be good. So in fact, the size of the successive state axiom are roughly comparable to the size of the effect axiom that you have. Okay, so how does this work? Well, it uses these three things. So one is that you can quantify overaction in the situation calculus. So if you think of, if I was doing this in propositional logic where I cannot quantify overthink, then this wouldn't work. Okay. The other thing that this uses is, well, it's assuming that relatively few actions will affect each fluent, which is true in any reasonable domain. Okay. Of course, you might imagine, well, have an action, the Big Bang occurred. Okay. Yeah, this will affect everything. But, you know, these are not the kind of domains that we're usually interested in reasoning about. Okay. In more realistic situations, it's true that few actions affect few fluents. And then it relies on another assumption that's a little bit more strong, which is basically that you can write down all the effects for all the actions that interest you. Okay, so your list of effects is complete. We'll see that, you know, this could be a problem if, you know, you want to be able to add action, you know, over time, or you know, add some new fluents that represent new property that didn't interest you before, but now they interest you. So you need to say that certain actions affect these properties. Okay. Okay, so let's see how that solution works. Hopefully we can get this covered before the end of this class. This simple solution to the frame problem, it's building on some previous work by Pedno, Haas, Schubert. Okay, and yeah, so basically, the writer solution involves three major steps. Okay, the first thing is to take the effect axiom that you have and rewrite them into a kind of normal form. Okay. The second step will be to make this assumption that now the effect that you have written down, they represent every situation where an action makes a fluent change value. So you have characterized all the effects for your domain. So that's this explanation closure. And then the last thing will be, from the result of two, then you essentially obtain some new axiom that you call successive state axiom that basically capture both the effect and nothing else changes. Okay. So let's go over these steps. So step one is basically you have to take the effect that you have and rewrite them for each fluent, you have to take every action that affects it and combine these effect axioms into axioms of this form. So on the right hand side, you have fluent F, some argument, do AF. Okay, and what you have on the left hand side is some condition. Okay, and this you have to capture every effect, every action that affects F and makes it true. And you have another one for every action and situation where that makes F become false. Okay. Here we're using, there could be more than one argument to F. Okay. So let's look at our example. Okay. So so we want to know which, so we want to write for self in, okay, what are these normal form effects for self in? So on the right hand side, we want self is in X and do AF. When is this clause to become true? Well, when A is go to X. Okay. Because this is the only action that we had, okay, that makes self in become true for something. What about the negative? So when does not self in X become true after doing A? Well, when you go to Y, and Y is different from X. Okay, so we rewrote what we had in the effect axiom. You know, you go back. This was our effect axiom for go to. Okay, so self-in is only affected by go to. It's not affected by open all doors. So this is the only thing we have to look at. And now we rewrote this to say, when does self-in become true? When I go to X, self-in X. And well, when does self-in X become false? Well, this part, when I go to some other room. Okay, so now I've written it. I have this for fluent self-in. So this condition now captures, I mean, we'll see the effect. So whenever, you know, this condition holds, self-in X becomes true, and whenever this condition holds, self-in becomes false. Okay. For open door, okay, what are the actions that can make this become true? Well, open all doors and the door is closed. If it was already open, it's not making it closed, open, it was already open. Okay. Can anything make open door become false? Not in this domain, because we don't have an action for closing door. Okay. So essentially you can think of this as an axiom that says false implies not open door to AF. Okay. It's a trivially satisfied. Okay. So this is the result of step one for this example domain. Okay. And now when you do this, you have to ensure that you remain consistent. So the condition for F to become true and the condition for F to become false, they should never be both true, because otherwise it would be like there's some situations where you do an action and makes F become both true and false. It's contradictory. Okay. And so here, you know, you can check that, you know, here, you know, the only one for which a self-in becomes true is the argument of the go to, and this says Y is different from, you know, so X is different from the Y that you went to. Okay, so it's consistent. Here's another example. Okay, so suppose that we have the following effect axiom for a fluent broken to become true. So the first one says, if the robot drop an object X, then X will become broken if X is fragile. Okay, so dropping an object which is fragile, it breaks. And this one says, if there's a bomb that explodes and the bomb is next to X in situation F, then X becomes broken. So suppose that these are the only effect axiom that you have where broken becomes true. Okay. So this means that if you want to put this in the normal form, you have to essentially, on the right hand side, you need broken X do AF. Then what do you have to have on the right hand side to be equivalent to this? Well, you can say if the action is drop or X, and X is fragile, then broken X do AF. So that's essentially equivalent to the first part. And the second part, if there exists a bomb and that bomb exploding and B is next to X and S, then X becomes broken. Okay, so I can take these two axioms and put them together, join them and put them together in this normal form. Okay, that's what you have to do in step one. Okay, so you take the effect axiom for every action that makes the fluent become true, and you combine them to get this normal form, positive effect axiom. Maybe for broken, we have a negative effect axiom that says, if the robot repairs X, then it becomes not broken. Okay, so I can put this in the normal form, and on the normal form, I have to have not broken X do AS. So this goes on to the left-hand side. So if the action A is some robot repairing X, then in do AS, X is not broken. Okay, so this is a second example of taking some effect axioms and putting them in this normal form. And you need to do this for every fluent. Okay. The second step is to say basically, so you're going to assume that the set of effect axiom that you wrote is complete. So there's no other effect that you forgot to write down about. Okay, because look, you want to say nothing else changed. Well, if you forgot to write something down where something changed, you're gonna have a problem. So you want to be able to make this completeness assumption. So these are your positive and negative normal form axiom for the fluent. Now you want to say that these captures all the ways in which F becomes true and all the ways in which F becomes false. What does that mean? Well, it means basically, my assumption is basically that if F was false and was made true by doing some action A, okay, then this condition must have been true, okay, because this condition captures all the ways in which from my effect axiom, I've specified that F becomes true, okay? So essentially the explanation closure assumption, I mean, for the positive case, it's this. It says that if F is false now in situation S, and it's true after do AS, then it must have been because this condition was true. It must have been because I had an effect axiom that said that, you know, it becomes true, and I compile it all into this normal form positive effect. Similarly, if F was true before and became false, okay, then if these axioms are complete, then it must have been because this condition was true. Okay, so F going from true in S to false in S must be because the condition for it to become false must have been satisfied. Otherwise, it means I forgot some effect. Okay,
Uh, first time, no, and then the situation must have been different from the second one, the true end, because
yeah, so this condition is about what action you're doing or occurred and what the situation before the action was. So if you go back and look at this, so it says that if the action is the robot dropping X and X was fragile before, then E becomes broken. X becomes broken. If X was next to a bomb and the action was the bomb exploding, it becomes broken after A. Okay, so and now it turns out that if you look at these explanation closure axioms, so essentially when you want to say that nothing else changed, you want to assume this. Okay, and these are essentially easily converted to frame axioms. So this is like saying, you know, if this, I believe this, then I also believe this because it's equivalent. This says that if F is false in S and this condition for it to become true is false, then it's still false afterwards. This one, if F is true in S and the condition for it to become false does not hold, then it remains true afterwards. Okay, so these frame axioms, these kind of general frame axioms are equivalent to these explanation closure axioms or assumptions. Okay, so now, you know, this we got from the effect axiom that we wrote down and we believe these. And now we say that we think these, we wrote down all the effects. So basically everything, whenever these conditions are false, things don't change. Okay. Then putting these together, you can rewrite this and this in this form. This says that F is true in do AS if and only if it became true, okay, because I did some action that made it become true in S, or it was already true in S, and I didn't do something that makes it become false. Okay, so essentially, I'm taking my generalized normal form axiom, positive and negative, together with the explanation closure and rewriting it to this equivalent form, which is a successive state axiom. And this kind of captures all the ways in which the fluent F can change value. Okay. Here, look at our example. So for our domain, we had these normal form effect axiom. So if you go to X, then the robot is become in X, self in X becomes true, and self in becomes false for whatever location you didn't go to. And this one says if you open all doors and a door is closed, it becomes open, and doors never become not open. So you can, this is basically, this condition is the phi plus for self in. This condition is the phi minus for self in. This condition is the phi plus for open. And false is the condition for phi minus for open. So you can rewrite, you get these successive state axioms. So self is in X in do AS if A is go to X, or if X is already in, self is already in X and S, and you didn't go somewhere else. Okay, self didn't go somewhere else. D is open in do AS if A is to open all doors and D was closed beforehand, or if it was already open. Okay, so see how short, how compact this is for specifying how these fluents change in this domain. Okay, and notice that this implies that if I do open all doors, self-in doesn't change. Okay, because if self-in X hold in self-in will hold in do AS if if I do open all doors, A is not equal to go to, so self-in is in do open all doors S hold if self-in XS, and this will be satisfied. It's not equal to go to. Okay, so it tells you implicitly that if you do an action that's irrelevant, the fluent doesn't change value. Okay, so imagine with the color of things not changing because you elect a new prime minister, or because you move to a different room, or then you would get that from these axioms. Yeah, so that's basically this writer solution to the frame problem. Maybe just to finish, one thing, I don't know, probably in previous courses you may have seen some work on planning, okay, where maybe you use PDDL to represent the planning domain. You use kind of strips format to represent the actions and so on. So in strips, you would have operators for an action like go to. So you would have an action, something like the robot goes from room F to room C using door D. You would have precondition, for this to be executable, F has to be, the agent self has to be in room F initially, and there's a door between F and T, and it's open. How do you represent the effects? Well, you say you add that self is in room T, the destination, and you delete the fact that self is in the initial room, the from room. Okay. So basically, how does the strips, this is kind of, the strips deal with the frame problem. This nothing else changes in the following way. It represents states as databases of atoms, okay? And the action effects are represented by updates to this database. Okay, you delete some fluents and you add some, or delete some atoms and add some atoms to this database that represents the state. And this is very simple, okay? But it only works if the state that you're starting with is completely known, okay? So in our example, if we say that we don't know whether the door from A to C is open, then you cannot apply this because you have two possible states, two possible models. Okay. In general, if you have a robot, there will be a lot of things that it doesn't know. So, you cannot apply this strip assumption and use the strip update method to, you might be able to apply if you enumerate all the possible states and look for, actions sequences that work in all these possible states, but tend to blow up, with logic, you can represent all these states compactly. And the other thing is that the strip doesn't really use a logic where you can reason about action. You sort of have a logic to describe states, but that's it. You cannot describe what sequence of state you might go through. Okay, so that's about strip. Okay, I'll stop here for today. Any questions? Okay, so I'll see you on Monday then, Monday at 3, I know at 5, and we'll continue with this, have a bit more material on reasoning about action.
Chi come prima c'è quando ti parlo della rubrica, quindi se il immediato fa non mi vedrai non c'è. Allá hay